You might like that stuff better.
Like that density thing.
Maybe not.
Oh, I would love to go on page 189. Look at that.
What is there nothing?
It's just a blank. I want to go to that page too.
God, what is happening?
Oh, I hate it when people write in math books. It's like, I want to do it on my own. Don't want your little notes.
All right, so we're going to start with the ones that have a graph like given to you. So number 2, so they're asking us to find the extreme values and where they occur. So you'll notice you have a graph that's from -1 to 1 on the x and the y. And you'll notice that there's some dots that are filled in and some that are open. That's also why I said to, because even if I attempted to put it up on the screen, you're not going to be able to see them. So we're looking for essentially the min and the max, if there are any, at each thing. So the mins and the maxes can only occur where there's like filled in circles. So the open circles don't work. So on number 2, the minimum would be at -1, 0. Because that's the closed in circle. That's why I was looking at it a minute ago and I was like, oh, it would be at also at what is that, 0, -1, and then I was like, nope, that's an open circle. So you just have to make sure you pay attention to that when they do that. So then the max, what do we think that would be at?
Whatever's like just to the left of 0, and I guess just under 1.
So the max would be at 1, 0. Just a point, can't have a max or a min, it's just a point.
So the min and the max have to be a closed thing.
So I guess for that one, it almost looks like we're looking for the x min and the x max.
Kinda, yeah. All right, 4, we're going to do the same thing. And remember, because we're just looking for extreme values, they didn't specify absolute, we're looking for all of them. So I think this one's all closed circles. Yes. All right, so what values look like they would be mins on here?
0, -1, and 2, 0.
Yep. What about maxes?
0, -3, and 1,
Okay, 1, 2 is yes. The other one, I think you said it backwards.
2. Oh, -3, 0. I didn't think about it.
That's why I was like looking at it. I was like, "There's not even a 3 on there."
If it makes you feel any better, I was confused on number 2 when she said -1, 0, because I was looking at that point that was 0, -1.
It's been a long break. It's okay. All right, so then 6, or well, identify each x value at which any absolute extreme values occur. Explain how your answer is consistent with the extreme value theorem. So the extreme value theorem should be written up here somewhere. I'm going to refer back to that real quick.
We could have our notes on that. No, I'm not sure if it would help.
So if f is continuous on a closed interval a to b, then f has both a max and a min value on the interval. Okay. So, and we're back. I mean, anybody watching the video is going to be like, what is she doing?
Such velocity.
All right, so number 6, we've got obviously the graph. We have endpoints at A and B. We have that other point C there in the middle. But notice that they are closed endpoints. Okay, there's no gaps in that function. So we have a max and a min. Okay, and we'll say what those are in just a second. Because the extreme value theorem applies. So we have a min and max. Okay, because it was continuous on that interval.
Is that E supposed to be curvy?
I always do my capital E's like that.
So it can just be a regular E.
Yes, I just write my capital E's funny. I don't do it every time, but I guess I'll fix it just for in case somebody's like, what's the special E?
Like me.
All right, so the max, we're looking at whatever the x value is of that point. So x equals what would be our max?
So are we going
What's
to
the highest point on the graph?
Okay, so it's E.
C. X equals C is the max.
I wasn't following because I wasn't sure if you were saying like the max X
Oh.
value. Because that would have been B.
And then what about the minimum? X equals what?
You got this one. Girl, what?
Wait, what?
The lowest value.
Oh,
Yeah,
B.
it's
Yes,
not the
X equals
value.
B.
Because I was still, I was thought, yeah.
You was thought.
I was confidently gonna say B for the last one. And then he was like laughing, said, I know it's about to, and I was like, why weren't we? Yeah.
It's alright.
8.
That's a good number. 2 cubed.
So with this one, what do we notice about this graph?
It has open
Dot, dot, dot.
circles.
So is this continuous?
No.
So does
Nah.
the extreme value theorem apply?
No.
No. So extreme value theorem does not apply because the function is not continuous or defined on a closed interval.
What class is that stuff for?
Algebra 1. Also, just to be clear with this problem, we can have a max and a min even if the extreme value theorem doesn't apply.
It's just not with those points that they've given us.
Well, not necessarily. So the problem with this is that it's not continuous and that the endpoints are open. So we don't have like a max or a min value. Now we could have had a min if they hadn't had that open circle at the bottom where it like turns and goes the other way. So like the next problem, number 10, what do you notice about that one?
It's one of those cusp dudes.
Yes. So what does that mean?
I don't remember.
Is it continuous?
No.
Well, I mean, there's a hole in it, so no.
No.
It is not continuous. So, whoops, wrong color. So the extreme value theorem does not apply. However, this one, we will have a max and a min. So our max is going to be at whatever the highest point is on our graph. The max is at x equals a because that's the highest point on the graph.
Because it's so high. You think about New Orleans.
That's the truth. What about our min?
Does it have to be a circle?
Do you have to be a circle?
Just has to be the lowest point on the graph.
C.
Yes.
I mean, just look at number 6. Was our max a circle?
I was paying attention. I was confused on that one.
Virginia.
I mean,
Supposed to
now
be
I
paying
understand.
attention.
No, I was paying attention. I was just
Stacy.
not fully there.
Well, you look like you're fully here, except for your hands.
Yeah,
They look like they're going through something.
they are
Not sure what. They're like,
a lot.
I don't know, like shedding a cocoon or something. Who knows? Maybe it'll be like one of them butterflies. Ooh, G of X.
All right, so these want us to find the extreme values of the function on the interval where they occur and identify any critical points that are not stationary points. I was trying to go back. So basically, we're going to take the derivative, set it equal to 0, and then we're going to be using the original and plugging in the endpoints to see if we have a max or a min at our endpoints, essentially. All right, so what is the, well, actually, let me back up. So this -1 less than or equal to x less than or equal to 1 is just telling us our closed interval from -1 to 1. Which you don't have to write that, but it might be helpful to see it that way. So I need the derivative of x, or of g of x. What would that be?
Negative x, e to the negative x.
Just negative e to the negative x. Remember, e to the x is just e to the x.
Right, so we don't do anything with the x. If there was
Correct.
a number on the x, we would put that out there. Okay.
Now, the other way we can write this, just as a refresher, is negative 1 over e to the x, like that. If it helps to think about it, it probably won't because it's an e, but sometimes it is useful. So making sure I was looking at the right problem. So now we use the endpoints, and we're going to plug those in, which I actually think for this problem we didn't need this, but that's fine. So into the original, g of -1 is e to the -1, or just e to the 1, which is e. So therefore, or well, I'm going to go back and write something there in a second. Let's do the other endpoint. Let's do the other endpoint first. So this is going to give me e to the -1, which is 1 over e. So we're determining min and max. So if, well, how do I want to do this? The book says one way to do this, but I actually usually do it the other way, so I'm going to show you both ways. Let me see where the... Went too far back.
Why did 3 dots mean that?
Therefore, I'm just going to write where the, like, what's a min and a max in just a second.
Wait, are you sure it's not there 3? You should have left it so fun. No, you're so funny.
Huh?
'Cause I have a quick comeback to that.
You're so funny.
Well, it's on everything. It's my mom. She says that. It's her
Wait,
quote.
I don't get it.
I'm quoting my mother.
No.
Okay, so...
About my parents.
Basically, because all we're dealing with is endpoints here, we can just look at, okay, which of these values is bigger and smaller, and we can determine the min and the max, which works great in this situation. Are you okay? However, this method does not work all the time. The other method of using the second derivative test does, so that's probably what I'm going to switch to in just a second, is going over to that method because I think it's easier to understand. That's why I went back. I was like, what are they using to determine? I was like, oh, right, it only works because there's only endpoints. Because are there any values of this that make this 0 that would be classified as a critical point? No. So if we set this derivative equal to 0, there's nothing that's going to make that 0. So that's why we're only using the endpoints. So this is going to be the max
I mean, if we throw in
At
some eyes.
x equals -1. And this is going to be a min at x equals 1.
Give the ease of eyes, then maybe you can see, you can find that.
So on the next one, just because it'll make sense to do it on the next one, I'll show you the second derivative test. Just to make it easier, not taking up too much time on one thing. (14) K of x equals e to the negative x squared, or from negative infinity less than x less than infinity.
I wonder why they chose K.
So, do I have endpoints here?
No.
No. So that means that I'm going to have to hope that there's a critical point, because, which there's going to be, since there's not, not that. But I'm going to have to make sure, okay, there's got to be a critical point because I don't have endpoints to work with. And that just doesn't make sense. So, I'm going to take the first derivative, which would be what? See how much you remember before break.
I'm gonna call this one negative e to the negative 2x.
No. Negative
Chain rule, maybe?
2x e to the negative x squared. So remember, the derivative of e to the whatever is always e to the whatever times the derivative of the whatever.
Now, see, that's what I tried to do on the one before, and it didn't work out like that, so.
It's because you did it wrong.
Yeah. I don't know. Virginia didn't even try.
Yeah, I let you have that. I'll see. I was just seeing if you knew how to do it.
I was gonna ask you to take it, because I, legit didn't know. That's one of those times that I actually didn't know. Should've let you take it.
One of the many times that you actually didn't know.
Actually didn't know. Actually, no. Okay, anyways. So, I'm going to, let's go ahead and take the second derivative also, just so that that's done, because that's normally what our second step would be. I have a feeling we're going to have to finish this problem tomorrow.
I'm crying.
let's do this. My iPad's not working. What is going on? Let's go ahead and set this equal to 0. Never mind. We'll just do it all tomorrow. We'll find the second derivative and set the first derivative equal to 0 tomorrow, so that we can show max, min, etc. There's not too many more problems in this section, so we should wrap it up tomorrow. Because like I said, a lot of what we did in the notes actually flows with kind of the rest of the chapter, so we should finish it up and y'all should have time to do a few things. We've just got the rest of 14, 18, 22, and 24, I think, as far as examples go, and then we'll be done.
Can I plug this into physics? I keep forgetting to charge it because I